800 million years after everything began, something impossible was growing in the dark. A black hole, 400 million times more massive than our closest star, hidden inside a galaxy barely visible to our most powerful instruments. James Webb just found it sleeping, not feeding, not glowing, just existing where nothing that enormous should be. Scientists thought black holes needed billions of years to reach this size. They were wrong. If you enjoy learning what lurks in the deepest corners of space, hit that like button and subscribe. This changes everything we thought we understood. Prepare yourselves. We begin. The telescope floated in perfect silence, 1 million miles from Earth, when its infrared sensors locked onto galaxy GN-1001830. Scientists were scanning the ancient universe, hunting for the usual suspects: bright, feeding black holes that glow like cosmic beacons. Instead, they found darkness. A specific kind of darkness that weighed 400 million times more than our closest star. The James Webb Space Telescope had detected something that should not exist, and the strange part was how quiet it appeared. Black holes announce themselves through violence. When they feed, surrounding gas spirals inward at tremendous speeds, heating to millions of degrees. The friction creates light so intense we can spot it across billions of light years. But this object produced barely a whisper. The team from Cambridge University analyzed the light spectrum, breaking it into wavelengths like splitting white light through a prism. They found patterns indicating rapid gas movement near an invisible center. The motion was unmistakable. Something massive was warping space itself. The galaxy existed just 800 million years after the Big Bang, during an era astronomers call the Cosmic Dawn. Back then, the universe was still clearing its fog. The first stars had only recently ignited. Galaxies were small and chaotic, nowhere near the organized spirals we see today. Finding any black hole from this period raises questions. Finding one this enormous and dormant defies conventional models entirely. Think of it like discovering a full-grown grizzly bear in a nursery. The timeline makes no sense. Standard theory suggests black holes grow gradually, starting small and accumulating mass over billions of years through steady feeding. This monster appeared to skip that entire process. Computer models show it would need the entire age of the universe at that point just to reach half its observed size through normal growth. Yet there it was, massive and eerily calm. The researchers used multiple camera filters to isolate the black hole's region from the surrounding galaxy. By comparing different wavelengths, they separated the faint signals coming from near the event horizon from the brighter light of stars in the outer galaxy. This technique revealed the true nature of what they were seeing. The black hole was consuming material at only 2.4% of its theoretical maximum rate. For something this enormous, that is practically fasting, scientists confirmed this finding through extensive computer modeling, running thousands of simulations to rule out alternative explanations. The data left no room for doubt. They had discovered the most massive dormant black hole ever observed in the early universe. Its host galaxy contained stars with a combined mass of about 830 million stellar masses. That ratio should not exist. But the numbers that revealed the galaxy's true secret were about to get even stranger. Black holes follow a speed limit. Scientists call it the Edington limit, named after British astrophysicist Arthur Edington, who calculated it nearly a century ago. When a black hole pulls in material, that material forms a disk that heats up dramatically. If the black hole tries to eat too fast, radiation pressure from the glowing disk pushes back, blowing away the very food the black hole wants to consume. Picture trying to drink from a fire hose. The force of the flow prevents you from actually getting water. This fundamental limit restricts how quickly any black hole can grow. Astronomers use this limit to calculate maximum growth rates. Feed a black hole steadily at this speed for the entire age of the early universe, and you get predictions for how large it could become. The dormant giant Webb discovered shattered those predictions by existing at all. 800 million years provides insufficient time to build something this massive through normal feeding. The math simply refuses to work. Roberto Maiolino, lead researcher from Cambridge's Kavli Institute for Cosmology, recognized the problem immediately. His team needed a new explanation. They could not ignore the observations. The black hole existed whether theories accounted for it or not, so they went back to their models and asked a different question. What if black holes do not grow steadily? What if they binge and sleep like hibernating animals? The simulations revealed a possibility. Black holes might exceed the Edington limit during brief, violent periods. For 5 to 10 million years, they would gorge themselves, growing at rates 2, 3, even 5 times the supposed maximum. Then something would change. The feeding frenzy would stop. The black hole would enter dormancy for roughly 100 million years. During these quiet periods, it would consume almost nothing, becoming nearly invisible to our telescopes. This pattern matches what bear researchers observe in nature. A grizzly will spend months eating constantly before winter, then sleep for half a year in its den. The sleeping period vastly outweighs the active period, but the intense feeding allows for survival and growth. Black holes might operate on cosmic timescales, using the same strategy. Feast explosively when conditions allow, then go dark. The ratio tells us something crucial about cosmic evolution. Dormancy lasts 10 to 20 times longer than hyperactive growth. If this model holds true, most black holes spend most of their existence in this quiet state. We have been looking at the universe during dinner time, assuming that is how black holes always appear. But dinner only lasts a fraction of their lives. The rest of the time, they are sleeping giants, hidden from even our most sensitive instruments, which raises an uncomfortable realization about everything else we might be missing. Grab a grain of sand. Now imagine something 400 million times heavier. The scale escapes human intuition. Our closest star weighs about 2 billion tons. Multiply that incomprehensible number by 400 million. You get a mass so extreme it bends space and time into a gravitational prison that nothing, including light, can escape. This is what Webb detected sleeping in the infant universe. To understand how enormous this truly is, consider that stellar mass black holes, the kind that form when massive stars die, typically weigh between 5 and 100 stellar masses. Supermassive black holes at the centers of large galaxies today range from millions to billions of stellar masses. The Milky Way's central black hole, confirmed through decades of observations, tracking stars orbiting it, weighs about 4 million stellar masses. That makes our galaxy's resident monster 100 times smaller than this ancient dormant beast. But size alone does not explain why this discovery disturbs astrophysicists. Context matters, age matters, distance matters. This black hole existed when the universe was only 6% of its current age. Galaxies were primitive. Cosmic structures had barely begun organizing. Finding something this developed this early is like discovering a skyscraper foundation in a Stone Age settlement. The technology, resources, and time required for such construction should not exist yet. The black hole's mass relative to its host galaxy reveals another problem. In the modern universe, supermassive black holes typically account for about 0.1% of their galaxy's total stellar mass. Scientists observe this ratio consistently across thousands of galaxies. It appears to be a fundamental relationship maintained by feedback mechanisms. Black holes grow, heat up surrounding gas, prevent star formation, limit their own food supply, and reach equilibrium with their host galaxy. This balance develops over billions of years. The dormant giant breaks this pattern spectacularly. Its mass equals roughly 40% of its galaxy's stellar mass, 400 times higher than the standard ratio. Imagine if your heart weighed 40% of your body weight. You would not function. Yet this system exists, captured in Webb's infrared images, defying expectations. The galaxy should have been torn apart. or consumed entirely. Instead, it continues forming stars, albeit slowly. Scientists measured these masses using spectroscopy, analyzing how light shifts due to motion. Gas orbiting the black hole moves at predictable speeds based on the gravitational force it experiences. Faster motion indicates stronger gravity, which means more mass concentrated in the center. The measurements were confirmed through multiple independent techniques. No room exists for misinterpretation. Something grew to monstrous proportions while its galaxy remained relatively small. And the way it accomplished this impossible feat reveals something even more unsettling about the universe's violent past. Picture the feeding process. Gas clouds drift toward the event horizon, accelerating to a fraction of light speed. Atoms collide with tremendous force, releasing energy as radiation. The accretion disk glows brighter than billions of stars combined. Material spirals inward, disappearing forever beyond the point where escape becomes impossible. This process can continue for millions of years, and during this time, the black hole is loud, bright, and unmistakable. Telescopes spot these feeding monsters across the entire observable universe. Then, something shifts. The black hole consumes most available material within its gravitational reach. Gas reserves dwindle. The accretion disk thins. Radiation pressure from the previous feeding frenzy has pushed surrounding clouds away, clearing a protective bubble around the black hole. Like a forest fire that burns so hot it creates its own firebreak, the black hole's own intensity has eliminated its food supply. The glow fades. The monster goes dark. This is dormancy. The black hole continues existing, its gravity still warping space, but without fresh material to consume, it produces almost no light. Detection becomes exponentially harder. Scientists can only find it through careful analysis of how its gravity affects nearby stars and gas. The dormant giant Webb discovered was consuming material at 2.4% of its maximum rate. For context, that is like a person eating 1 meal per month instead of 3 per day. Barely enough to register. Ignas Georgibalis, the Cambridge researcher who led the detection, described the challenge of finding such objects. Even though this black hole was enormous, its dormant state made it nearly invisible. Only its extreme mass allowed detection at all. Smaller dormant black holes from the same era would remain completely hidden with current technology. The team got lucky. They were scanning a region of space containing only 35 galaxies. Finding a dormant supermassive black hole in such a small sample suggested these objects might be everywhere. The dormancy cycle explains a major mystery. If black holes spent their entire lives feeding actively, we should see far more of them glowing in the distant universe. Instead, we find relatively few compared to the number of galaxies that should host them. The numbers never balanced. But if black holes spend 90 to 95% of their existence in quiet states, suddenly the math works. We are simply looking at them during their off hours. Think of it like trying to count bears by only looking for active, feeding bears. You would dramatically underestimate the population because most bears are sleeping, hiding, or traveling. The visible ones represent a small fraction of the total. The same principle applies to black holes. For every active, glowing monster we detect, dozens or hundreds might be sleeping nearby, which means our census of the early universe's black hole population could be off by orders of magnitude. And what that implies about cosmic structure is about to become clear. Galaxy GN-1001830 appeared unremarkable at first glance. Small, red, faint. The researchers catalogued it as part of the JADES survey, which stands for James Webb Advanced Deep Extragalactic Survey. This program specifically targets early universe galaxies, pushing the telescope's infrared capabilities to their limits. Thousands of ancient galaxies have been identified this way. Most follow expected patterns. This one harbored a secret. The galaxy contained stars with a combined mass of roughly 830 million stellar masses. For comparison, our Milky Way contains about 200 billion stellar masses. This early galaxy was tiny, a cosmic infant still in development. Star formation was occurring, but slowly compared to other galaxies from the same era. Scientists measure star formation rates by analyzing specific wavelengths of light emitted by hot young stars. This galaxy was producing new stars at a suppressed rate, as if something was throttling the process. That something was the black hole. 400 million stellar masses concentrated in the galaxy's core. The ratio was staggering. Imagine a town where the town hall weighs more than all the houses, businesses, and infrastructure combined. The balance makes no sense. In healthy galaxies, the central black hole grows in proportion to the galaxy itself. They co-evolve through feedback mechanisms. The black hole heats surrounding gas through radiation and winds, regulating star formation. More stars means more gas, which feeds the black hole, which heats more gas, which limits star formation. An equilibrium emerges. This galaxy never reached equilibrium. The black hole grew to dominate its host before feedback mechanisms could establish balance. How this happened remains unclear. One theory suggests the black hole formed first, through direct collapse of a massive gas cloud, before stars even began forming. Another possibility involves a merger. Perhaps several smaller black holes collided and combined early in the galaxy's history, creating a single massive object. Or maybe the galaxy experienced an unusually dense concentration of gas that allowed rapid growth. Scientists use spectroscopic measurements to determine both masses with high precision. The technique involves analyzing Doppler shifts in light from moving gas. Material orbiting the black hole shows different shifts than material in the outer galaxy. By mapping these velocity patterns, researchers reconstructed the mass distribution. The numbers were consistent across multiple measurement methods. No error could account for such an extreme ratio. The suppressed star formation rate provides a clue. Black hole winds and radiation heat interstellar gas, preventing it from cooling and collapsing into new stars. A hyperactive black hole could effectively shut down star formation across an entire galaxy. But this black hole was dormant. The suppression must have occurred earlier, during its active feeding phase. The galaxy still shows the scars of that violent period. And buried in those scars lies evidence of something even more extreme. Light is the only messenger we have from distant space. We cannot send probes to galaxies billions of light years away. We cannot measure their properties directly. Everything we know comes from analyzing light that has traveled across the universe for unimaginable durations. Black holes complicate this process by producing almost no light when dormant. They become cosmic ghosts, detectable only through their gravitational influence on surrounding material. Active black holes glow brilliantly. Their accretion disks reach temperatures exceeding 10 million degrees. At these extremes, atoms stripped of electrons emit X-rays, ultraviolet radiation, and visible light across the spectrum. Quasars, the brightest active black holes, can outshine their entire host galaxy. Some produce luminosity equivalent to 10 trillion stars. We can spot these cosmic lighthouses from the edge of the observable universe. They are impossible to miss. Dormant black holes offer no such convenience. Without an accretion disk, they produce almost no radiation. Their event horizons, the boundaries beyond which nothing escapes, remain dark and silent. Detection requires indirect methods. Scientists look for stars orbiting an invisible point, their paths bent by gravity. They search for gas moving at high speeds near galactic centers, indicating something massive is pulling it. They analyze distortions in light from background objects, caused by gravitational lensing. The Webb telescope's infrared capabilities proved crucial for this discovery. Infrared light penetrates dust clouds that block visible light. Early universe galaxies are heavily obscured by dust, making them difficult to study with optical telescopes. Webb's instruments can peer through these veils. revealing structures hidden from view. The telescope also detects red-shifted light from extremely distant objects. As the universe expands, light stretches to longer wavelengths. Objects from the early universe emit visible and ultraviolet light that arrives at Earth as infrared by the time it reaches us. The research team used a technique called spectroscopy to identify the black hole. They split the galaxy's light into its component wavelengths, creating a spectrum similar to a rainbow but with far more detail. Specific elements produce characteristic patterns, like fingerprints, that reveal temperature, density, and motion. The spectrum showed gas moving at thousands of miles per second near the galaxy's center. Only a massive black hole could accelerate material to such speeds. But here is the limitation. This black hole was only detectable because of its enormous mass. Smaller, dormant black holes would produce weaker gravitational effects, making them effectively invisible with current technology. Scientists estimate that countless dormant black holes from the early universe remain undetected simply because they are not massive enough to reveal themselves. Each discovery of a sleeping giant suggests dozens more lurk just beyond our detection threshold, which raises a question that should unsettle anyone thinking about cosmic surveys and maps. Numbers tell the story. The black hole was feeding at 2.4% of its theoretical maximum rate. Scientists confirmed this by measuring the luminosity of the accretion disk and comparing it to predictions based on the black hole's mass. The calculation is straightforward. More mass consumption equals more heat, which equals more light. Less light means less active feeding. The measurements were precise and repeated multiple times. The black hole was barely eating. For context, an active supermassive black hole typically feeds at 10 to 100% of its Edington limit. These objects glow brightly, heating surrounding gas to millions of degrees. Their accretion disks extend outward for billions of miles, swirling like cosmic hurricanes. Material spirals inward at a fraction of light speed, releasing tremendous energy before crossing the event horizon. This energy output can be so intense it affects galaxy evolution across millions of light years. The dormant giant showed none of this activity. Its accretion disk was faint, cool, and thin. Gas trickled inward at a leisurely pace. No powerful winds blew outward. No jets of energetic particles shot from the poles. The black hole simply sat there, its gravity pulling on nearby material with insufficient force to create dramatic effects. It was starving, not by circumstance, but apparently by design. The feeding frenzy had ended. Dormancy had begun. This low accretion rate explains why the discovery was so difficult. Luminosity drops exponentially as feeding slows. A black hole, consuming at 3% capacity, produces roughly 30 times less light than one feeding at maximum rate. That reduction makes it orders of magnitude harder to spot. The researchers had to analyze extremely faint signals, teasing out subtle patterns from noisy data. One wrong assumption would have caused them to miss it entirely. The timing of dormancy appears related to environmental conditions. When the black hole exhausted nearby gas reserves, feeding naturally slowed. Radiation pressure from earlier active periods had pushed remaining clouds away, creating a cleared zone. New gas would eventually drift inward through gravitational attraction, but this process occurs slowly. The black hole might remain dormant for 100 million years before enough material accumulates to restart vigorous feeding. Scientists ran simulations to test whether this 2.4% rate matched predictions. They modeled gas dynamics around massive black holes in early universe conditions. The results aligned with observations. After a hyperactive growth phase, black holes would naturally enter a quiescent state lasting many times longer than the active period. The ratio matched perfectly. Feast for 5 to 10 million years, sleep for 100 million. During sleep, consume at minimal rates just sufficient to prevent complete shutdown. And the evidence supporting these massive feeding binges is about to become impossible to ignore. Imagine trying to explain how a mountain formed by only watching it for 1 second. you would see no change, no growth, nothing to indicate the violent geological processes that built it over millions of years. This is the challenge astronomers face when observing black holes. We catch brief snapshots of objects that evolve over timescales far exceeding human civilization. Drawing conclusions requires models and simulations that fill gaps between observations. The dormant giant forced scientists to reconsider those models entirely. Standard theory suggested black holes grow through steady accretion. Gas flows inward at rates determined by the Edington limit, producing consistent luminosity over time. This model worked for nearby galaxies, where we can observe black holes across millions of years through multiple observations. But it failed spectacularly when applied to the early universe. Black holes there appeared too massive too quickly. The numbers refused to balance. Roberto Maiolino and his team proposed a radical alternative. What if black holes grow in bursts? Short periods of extreme feeding, exceeding the Edington limit by factors of 2 to 5, followed by long dormant phases. During hyperactive periods, the black hole would ignore normal limits. Radiation pressure would still push outward, but somehow the inflow would overwhelm that pressure, allowing rapid mass accumulation. Then, suddenly, the feeding would stop. The black hole would go dormant, consuming almost nothing. Computer simulations tested this hypothesis. The team modeled gas dynamics around supermassive black holes in early universe conditions. They varied parameters: gas density, temperature, black hole spin, magnetic fields, radiation pressure. Some combinations produced steady feeding, others produced bursts. The burst scenarios matched observations perfectly. A black hole could reach 400 million stellar masses in less than 1 billion years if it experienced multiple hyperactive episodes interspersed with dormancy. The burst model explains several puzzling observations beyond this single discovery. Webb has found dozens of supermassive black holes in the early universe, many appearing oversized relative to their host galaxies. If these objects grew steadily, they should not exist. If they grew in bursts, the pattern makes sense. We are catching them at different phases, some actively feeding, bright and obvious, others sleeping, faint and hidden. The dormant ones remain largely uncounted, but they must be there. Evidence for bursts comes from the galaxy's star formation history as well. Spectroscopic analysis reveals that this galaxy formed most of its stars in brief, intense episodes rather than gradually over time. The pattern mirrors the proposed black hole behavior: rapid growth, then quiescence. The galaxy and black hole might have experienced synchronized burst cycles, each affecting the other through feedback. When the black hole fed vigorously, it heated gas and suppressed star formation. When it went dormant, stars could form again briefly before gas reserves depleted. A cosmic rhythm playing out over hundreds of millions of years, but the specific time frame of these feeding frenzies reveals something even more extreme: 5 million years. That is the estimated duration of a hyperactive black hole feeding episode. For perspective, humans have existed for roughly 200,000 years. Recorded history spans about 5,000 years. A single black hole feeding frenzy lasts 1,000 times longer than all of human civilization. Yet, in cosmic terms, 5 million years is a blink. The universe is nearly 14 billion years old. These feeding bursts represent less than 0.1% of cosmic history. During these periods, physics operates at extremes. Gas collapses inward faster than normal stability would allow. The black hole's gravity overwhelms radiation pressure that usually limits growth. Think of a dam breaking. Water that accumulated slowly behind the barrier suddenly rushes through all at once. The burst cannot be sustained indefinitely, but while it lasts, the flow rate exceeds anything possible under normal conditions. Black holes experience the gravitational equivalent. What triggers these episodes remains uncertain. One possibility involves galaxy mergers. When two galaxies collide, their gas clouds slam together, compressing and heating. This collision funnels enormous amounts of material toward the central black holes of both galaxies. If those black holes merge, the resulting combined object might enter a hyperactive feeding state, consuming the newly available gas at tremendous rates. This would explain why early universe black holes grew so quickly. Galaxy mergers were far more common when the universe was young and dense. Another trigger might be instabilities in the accretion disk itself. Under certain conditions, the disk can fragment, forming dense clumps of gas that spiral inward rapidly. These clumps bypass normal accretion processes, delivering mass directly to the event horizon. Computer simulations show this fragmentation occurs more readily in the turbulent, gas-rich environments of early universe galaxies. The process is violent, chaotic, and temporary. Once fragmentation ends, normal feeding resumes at much lower rates. The growth achieved during these 5 to 10 million year bursts is staggering. A black hole feeding at 5 times the Edington limit can double its mass in roughly 10 million years. Multiple episodes could build a 400 million stellar mass monster from a much smaller seed in less than 1 billion years. The math finally works. You do not need billions of years of steady growth. You need a few brief episodes of explosive growth separated by long dormant periods. Scientists measured the likely duration of these bursts using theoretical models of gas dynamics and radiation pressure. The calculations indicate that feeding above the Edington limit becomes unstable after 5 to 10 million years. The black hole heats surrounding material so intensely that it blows away its own food supply. The accretion disk disintegrates. Gas clouds scatter. The burst ends abruptly, leaving the black hole to sleep while new material slowly accumulates. And the length of that sleep cycle reveals something unexpected about cosmic time itself. 100 million years. The dormant period dwarfs the active phase by a factor of 10 to 20. Think about that ratio. If you spent 2 hours eating, you would then sleep for 20 to 40 hours before eating again. This is how black holes apparently live their lives. Brief, frantic feeding, followed by extended dormancy. The pattern repeats across cosmic history, cycling through phases we are only beginning to recognize. The dormancy occurs because black holes exhaust their food supply during hyperactive episodes. Gas within gravitational reach gets consumed or blown away. The surrounding region becomes depleted. New material must drift inward through slower processes. Gravity alone is not enough. Gas clouds in space have their own motion, their own angular momentum. They orbit the galactic center rather than falling straight in. Converting orbital motion into inward spiral takes time. Friction between gas clouds gradually removes energy, allowing them to drift closer, but this process is slow. During the 100 million year nap, the black hole continues pulling on distant gas clouds. Gradually, incrementally, material edges closer. Think of water draining from a bathtub. At first, water near the drain flows out quickly, but water on the opposite side of the tub moves slowly, taking time to cross the distance. Black holes experience something similar. Nearby gas disappears rapidly during active feeding. Distant gas takes ages to arrive. The black hole must wait. Environmental factors affect dormancy duration. In gas-rich environments, new material arrives faster. The dormant period might last only 50 million years. In gas-poor regions, dormancy could extend for 200 million years or longer. The 100 million year estimate represents an average based on early universe conditions. Those conditions favored relatively rapid replenishment because galaxies were smaller, denser, and contained more gas overall. Modern galaxies have larger, more diffuse structures, where gas takes longer to reach central black holes. The long dormancy explains why we have missed so many black holes in surveys. If dormancy lasts 10 to 20 times longer than active feeding, then at any given moment, 90 to 95% of black holes should be sleeping. We have been counting only the active ones, the 5 to 10% that happen to be feeding when we look. The dormant majority remains invisible, hiding in plain sight. Our census of cosmic black holes is incomplete by roughly an order of magnitude. This has profound implications for understanding galaxy evolution. Black holes influence their host galaxies primarily through feedback during active periods. They heat gas, drive winds, suppress star formation. But if black holes spend most of their time dormant, then this feedback operates intermittently rather than continuously. Galaxies experience long, quiet periods, interrupted by brief episodes of intense black hole activity. This episodic pattern shapes how galaxies grow and evolve, and it explains some puzzling observations about why galaxy properties vary so dramatically even among similar systems. However, accepting this new model requires abandoning theories that have guided astronomy for decades. Black holes were supposed to start small. The standard model suggested they form from collapsed massive stars, beginning with masses between 10 and 100 stellar masses. These seed black holes would then grow gradually through accretion and mergers, reaching supermassive status after billions of years. This model worked beautifully for explaining black holes in the local universe. It failed completely when applied to objects like the dormant giant Webb discovered. The timeline does not work. 800 million years after the Big Bang is not enough time to build a 400 million stellar mass black hole through standard growth mechanisms. Even feeding at the Edington limit continuously, a stellar mass black hole cannot reach such sizes that quickly. The math is unforgiving. Either the black hole started much larger than stellar collapse allows, or it grew much faster than the Edington limit permits. Both possibilities break conventional theory. One alternative proposes direct collapse. Instead of forming from a single massive star, perhaps some black holes form when entire gas clouds collapse at once. Under special conditions in the early universe, clouds containing 100,000 to 1 million stellar masses might collapse directly into black holes without first forming stars. This would create massive seeds, bypassing the slow growth problem. These seeds could then grow to supermassive status within the available time frame. Direct collapse requires very specific conditions. The gas cloud must be extremely hot to prevent fragmentation into individual stars. It must be metal poor, containing almost no elements heavier than hydrogen and helium. Heavy elements cool gas efficiently, promoting star formation. Pristine gas remains hot longer, allowing collapse into a single massive object. These conditions existed in pockets of the early universe, particularly in regions where intense radiation from nearby galaxies kept the gas hot. Another possibility involves primordial black holes, hypothetical objects that formed in the first moments after the Big Bang from density fluctuations in the primordial plasma. These black holes could have any mass, from microscopic to astronomical, depending on the size of the density fluctuation. If million stellar mass primordial black holes existed, they could serve as seeds for rapid growth into supermassive black holes. However, no confirmed observations of primordial black holes exist. They remain theoretical. The burst feeding model offers a third path. Start with moderately sized seeds, perhaps 1,000 to 10,000 stellar masses, formed through either direct collapse or massive star clusters. Then grow them through multiple hyperactive episodes, each briefly exceeding the Edington limit. This approach requires no exotic physics. It simply allows temporary violation of steady-state assumptions. The black hole grows rapidly during bursts, slowly between bursts, and spends most of its time dormant. The model matches observations without invoking unproven mechanisms. Yet, accepting it means rewriting textbooks and reconsidering decades of research. And the host galaxy itself holds clues that make this rewrite unavoidable. Galaxy GN-10011830 was dying. Not dead, but dying. Star formation continued, but at a fraction of the rate observed in similar galaxies from the same era. Scientists measured this by analyzing light from hot young stars, which emit specific wavelengths of ultraviolet radiation. The galaxy's spectrum showed these signatures, confirming star formation was occurring, but the intensity was weak. Something was suppressing the process. Black hole feedback provides the most likely explanation. During its active feeding phases, the massive black hole would have heated surrounding gas through radiation and powerful winds. When gas heats above certain thresholds, it cannot cool and collapse to form stars. The pressure from heat prevents gravitational collapse. The galaxy becomes starved of raw material for star formation. This suppression continues even after the black hole enters dormancy, because the gas remains hot for tens of millions of years. Astronomers call these suppressed galaxies quenched. The term describes galaxies where star formation has been shut down or severely reduced. Quenching typically occurs in older, more evolved galaxies where gas reserves have been depleted naturally over time. Finding a quenched galaxy in the early universe is unusual. The universe was gas-rich back then. Galaxies should have ample material to form stars vigorously. The presence of the oversized black hole explains the anomaly. The suppressed star formation rate tells us something about the black hole's history. It must have experienced one or more hyperactive feeding episodes relatively recently. During these episodes, it would have pumped enormous energy into surrounding gas, heating it and driving it outward through powerful winds. These winds are no gentle breeze. They reach speeds of thousands of miles per second, carrying enough momentum to blow gas completely out of the galaxy. Once expelled, that gas cannot form stars. Over time, expelled gas can cool and fall back into the galaxy. Gravity eventually wins, but this process takes tens or hundreds of millions of years. Currently, we are seeing the galaxy in a recovery phase. Gas is gradually cooling and condensing. New stars are forming, but slowly. The black hole remains dormant, no longer pumping energy into the system. Star formation will likely increase as more gas cools and becomes available. The galaxy might experience a burst of star formation before the black hole wakes up and quenches it again. This cyclical pattern, black hole activity followed by quenching, followed by recovery, followed by renewed activity, might be common in galaxy evolution. Galaxies do not grow smoothly. They experience punctuated equilibrium, long periods of stability, interrupted by brief dramatic changes. The black hole drives these changes through feedback. When it feeds, it suppresses stars. When it sleeps, stars can form. The cycle repeats across cosmic history, shaping galaxy properties in ways we are only beginning to understand. And the light carrying this story has been traveling toward us for a very long time. Light from galaxy GN-10001830 began its journey when the universe was young. For 800 million years, it traveled through expanding space, crossing distances our minds cannot truly grasp. Each photon carried information encoded at the moment of emission. When those photons finally struck Webb's mirrors, they told a story written in spectral lines. Scientists just had to learn how to read it. Spectroscopy works by splitting light into its component wavelengths. Different elements and molecules absorb or emit light at specific, characteristic wavelengths determined by quantum mechanics. Hydrogen produces one pattern. Oxygen produces another. Carbon, nitrogen, iron, each has its own fingerprint. By identifying which wavelengths are present or absent in a spectrum, scientists determine composition, temperature, density, and motion of the emitting material. The research team used Webb's near-infrared spectrograph to analyze the galaxy's light. The instrument split incoming photons across a detector array, creating a detailed spectrum spanning wavelengths from 0.6 to 5.3 microns. This range captures light that was emitted in ultraviolet and visible wavelengths, but has been redshifted to infrared by cosmic expansion. The spectrum revealed multiple emission lines characteristic of hot gas orbiting a massive object. One particular set of lines proved crucial. Hydrogen emission from gas near the black hole showed what astronomers call broad line profiles. Instead of appearing as sharp, narrow features, these lines were smeared across a range of wavelengths. This broadening occurs when gas moves at high speeds relative to the observer. Some gas moves toward us, shifting light to shorter wavelengths. Some moves away, shifting to longer wavelengths. The result is a broad, spread-out line. The width of the broadening directly indicates velocity. The measurements showed gas moving at thousands of miles per second. Only a black hole with mass in the hundreds of millions of stellar masses could accelerate material to such speeds through gravity alone. Stars and gas clouds in the outer galaxy moved much slower, at hundreds of miles per second. The velocity difference proved that something extremely massive occupied the galactic center. Combined with the low luminosity of the accretion disk, this pointed unambiguously to a dormant supermassive black hole. Additional spectral features revealed the galaxy's star formation rate and stellar population age. Young stars emit strong ultraviolet radiation that ionizes surrounding hydrogen, producing characteristic emission lines. Old stars produce different signatures. By comparing relative strengths of various lines, researchers reconstructed the galaxy's history. It had formed most of its stars in an earlier burst, followed by a period of reduced formation. The pattern matched predictions for a galaxy affected by black hole feedback. Every line in the spectrum contributed evidence, building a comprehensive picture from wavelengths of light. But interpreting those wavelengths required sophisticated computer models. The team needed to test whether their observations made physical sense. Could a black hole this massive actually exist at this early time? Could it be dormant? What mechanisms would explain its formation and growth? These questions required more than observational data. They demanded detailed simulations, modeling gas dynamics, radiation physics, and gravitational interactions over hundreds of millions of years. Computers became time machines, running cosmic history forward to see what patterns emerged. The simulations started with initial conditions matching the early universe 800 million years after the Big Bang. High gas density, low metallicity, turbulent flows driven by gravitational collapse of dark matter halos, small galaxies forming from condensing gas clouds. Black hole seeds scattered throughout the simulation volume. The team ran multiple versions, varying parameters to explore different scenarios. Some simulations assumed small seeds from stellar collapse. Others used massive seeds from direct collapse. Each version evolved forward in time. Supermassive black holes grow through two mechanisms, accretion and mergers. Accretion occurs when gas falls onto the black hole, increasing its mass gradually. Mergers occur when two black holes combine during galaxy collisions, adding their masses together instantly. The simulations tracked both processes, calculating how quickly black holes grew under different assumptions. Standard accretion at the Edington limit produced undersized black holes. They could not reach observed masses in the available time. The numbers refused to work. The breakthrough came when the team allowed super Edington accretion during brief episodes. They programmed the simulations to trigger rapid growth phases when gas density exceeded certain thresholds. During these phases, accretion rates jumped to 2, 3, or 5 times the Edington limit. The black hole would grow explosively for 5 to 10 million years, then enter dormancy as surrounding gas depleted. This pattern repeated multiple times as the galaxy experienced mergers and gas inflows. After several burst cycles, the simulation produced black holes matching observed properties. The simulations also predicted the ratio of active to dormant black holes at any given time. Since dormancy lasted 10 to 20 times longer than active feeding, 90 to 95% of black holes should be sleeping. This matched the detection statistics. Finding one dormant black hole among 35 surveyed galaxies suggested roughly 3% were active. The numbers aligned perfectly. The burst model not only explained individual observations, but predicted population statistics. Additional simulations explored how black hole feedback affected star formation. When black holes fed actively, they heated surrounding gas and drove powerful winds. Star formation dropped dramatically during these episodes. When black holes went dormant, star formation could resume at higher rates. The cycle produced galaxies with suppressed star formation, matching observations of GN-1001830. Every aspect of the data fit the model. Computer predictions matched reality, but some numbers in that reality were more shocking than others. Take any nearby galaxy, measure its total stellar mass, measure its central black hole mass, divide the second by the first. The answer will be roughly 0.1%, give or take a factor of a few. Astronomers have checked this ratio in thousands of galaxies. The consistency is remarkable. Black holes always represent a tiny fraction of their host galaxy's mass. This relationship appears fundamental, maintained by feedback mechanisms that couple black hole growth to galaxy evolution. The dormant giant breaks this rule spectacularly. Its mass equals 40% of the host galaxy's stellar mass, 400 times higher than the standard ratio. If galaxies were countries and black holes were governments, this would be a government outweighing all its citizens, infrastructure, and resources combined. The comparison is absurd, yet the measurements are solid. Multiple independent techniques confirm the masses. The ratio is real. How did this happen? One possibility is that the black hole formed first and the galaxy formed around it. Direct collapse could have created a massive black hole seed before significant star formation occurred. As gas condensed around this seed, some formed stars while some accreted onto the black hole. If the black hole grew faster than the galaxy, the ratio would become skewed. This scenario requires very specific conditions but remains physically plausible. Another explanation involves the galaxy losing stellar mass. Perhaps the black hole's powerful winds during active feeding episodes ejected not just gas but also stars. The gravitational binding energy of small galaxies is relatively weak. Strong enough winds could strip stars from the outer regions, reducing the galaxy's total stellar mass. This would increase the black hole to galaxy mass ratio without requiring the black hole to grow unusually fast. The expelled stars would now orbit the galaxy in a diffuse halo, making them difficult to detect. A third possibility is that we are seeing the galaxy at a special moment in its evolution. The black hole grew rapidly during recent hyperactive episodes, while star formation was suppressed by feedback. Over the next billion years, the galaxy might accumulate more stars as the black hole remains dormant. Eventually, the ratio would decrease towards standard values. We are catching it out of equilibrium during a transitional phase. The timing is coincidental, but early universe observations inherently select for unusual objects because everything was more extreme back then. Regardless of the explanation, the ratio tells us that black holes and galaxies do not always grow in lockstep. The coupling can break under certain conditions, allowing one component to dominate the other temporarily. This flexibility challenges simple models of coevolution. Galaxy formation is messier, more chaotic, and more varied than idealized scenarios suggest. The early universe produced structures we are still learning to explain, and each new discovery suggests there are far more of these extreme objects hiding in the darkness. Statistics rule the cosmos. When you find one rare object, probability theory tells you how many more exist beyond detection limits. The calculation is straightforward. The team surveyed 35 galaxies in a small patch of sky. They found one dormant supermassive black hole. If this sample is representative, roughly 3% of similar galaxies should host detectable dormant black holes. But detection was only possible because this particular black hole was extremely massive. Smaller dormant black holes would produce weaker signals. Their gravity would affect fewer stars, moving them at lower speeds. The spectroscopic signatures would be fainter, harder to distinguish from noise. Current technology can detect dormant black holes above approximately 100 million stellar masses if they are sufficiently distant. Below that threshold, they become invisible. The dormant giant at 400 million masses was comfortably above the detection limit. But what about black holes with masses of 50 million, 20 million, or 10 million? Computer simulations show these smaller, dormant black holes should be far more common than massive ones. The mass distribution of black holes follows a power law. For every object with mass m, there should be roughly 4 to 10 objects with mass m divided by 2. Apply this relationship recursively, and you find that smaller black holes vastly outnumber larger ones. If one 400 million stellar mass dormant black hole exists in this survey volume, there should be dozens of 100 million stellar mass dormant black holes and hundreds of 10 million stellar mass dormant black holes in the same region. None of those smaller objects would be detectable with current methods. They are there, warping space with their gravity, influencing their host galaxies through feedback, but producing too little light to spot. We are seeing only the tip of the iceberg. The 3% detection rate applies only to the most massive dormant black holes. The true dormant population could be 10, 20, or 50 times larger. The early universe might be saturated with sleeping giants. This changes cosmic census estimates fundamentally. Previous surveys counted active black holes and assumed dormant ones were rare or absent. If dormancy is the default state and active feeding is the exception, then black holes are far more common than we thought. Nearly every early universe galaxy might host a supermassive black hole, most of them sleeping. The implications for galaxy evolution are profound. Black hole feedback shapes galaxy properties primarily through these hidden objects. Future surveys with more sensitive instruments might find some of the missing population. The European Extremely Large Telescope, currently under construction, will have greater light gathering power than Webb. It might detect dormant black holes down to 50 million stellar masses, but even this improvement will miss the majority. Most dormant black holes will remain hidden indefinitely, their existence inferred statistically rather than observed directly. We are exploring a universe where most of the players stay invisible, which raises an important question about how these invisible monsters first came into existence. The early universe was nothing like today's cosmos. No organized galaxies, no heavy elements, just clouds of primordial hydrogen and helium collapsing under their own gravity. Imagine a fog gradually condensing into droplets, then streams, then rivers of gas flowing toward points of maximum density. Gravity amplified tiny initial irregularities into massive structures. This was not a gentle process. Gas clouds collided at speeds exceeding thousands of miles per second. Shock waves heated material to millions of degrees. The violence was universal and ongoing. Dark matter drove the collapse. This invisible substance, 5 times more abundant than normal matter, clumped first because it does not interact with radiation. Dark matter halos formed early, creating gravitational wells. Normal matter fell into these wells, heating as gravitational potential energy converted to thermal energy. In most regions, this heat prevented runaway collapse. Gas would heat, expand, cool slowly through radiation, then collapse again in cycles. Star formation proceeded gradually through fragmentation of gas clouds into smaller clumps. But some regions experienced different fates. If gas remained exceptionally hot, fragmentation could not occur. Without fragmentation, the entire cloud collapsed as one. The result was either a supermassive star, which would quickly collapse into a black hole, or direct collapse into a black hole without ever forming a star. These direct collapse scenarios required specific conditions: pristine gas with almost no heavy elements, intense radiation keeping the gas hot, and rapid inflow preventing cooling. Such conditions existed in pockets throughout the early universe. Scientists refer to these events as direct collapse black holes. They would have masses between 10,000 and 1 million stellar masses immediately upon formation. This provides the massive seeds needed to explain early supermassive black holes. Starting from such large initial masses, growth to hundreds of millions of stellar masses becomes achievable within 800 million years, even without super Edington accretion. Add in burst feeding episodes, and the process accelerates dramatically. Evidence for direct collapse comes from multiple sources. Simulations show it occurs naturally in early universe conditions. Observations of distant quasars suggest black hole masses inconsistent with growth from stellar mass seeds, and discoveries like the dormant giant require either massive seeds or extreme growth rates. Direct collapse provides both. The process was probably common during the first billion years, creating a population of intermediate mass black holes that served as seeds for later growth. The violence of these formation events shaped everything that followed. Direct collapse black holes would have immediately begun accreting surrounding gas, driving powerful winds and heating their environments. This feedback affected how galaxies formed around them. The black holes were not passengers in galaxy evolution, they were drivers, fundamentally shaping the structures we observe today. And understanding how they concentrated mass before galaxies even fully formed reveals something profound about cosmic structure. Gravity does not wait for permission. The moment matter exists, gravity begins pulling it together. In the early universe, this process operated at maximum efficiency because everything was closer together. The universe was smaller, denser, more concentrated. Dark matter formed the scaffolding, creating invisible frameworks where normal matter would accumulate. These dark matter halos acted like gravitational traps, funneling gas toward their centers with relentless inevitability. Picture water flowing downhill. It follows the path of least resistance, converging in valleys and low points. Gas in the early universe behaved similarly, flowing along gravitational gradients toward regions of highest density. But unlike water, gas can heat up through compression. As it flowed inward, friction between clouds and gravitational compression raised temperatures. Hot gas resists collapse through pressure. The process became a battle between gravity pulling inward and pressure pushing outward. In most cases, pressure won temporarily. Gas would heat, stabilize, cool through radiation, then collapse again in stages. This stepwise process allowed gas to fragment into smaller clouds that became individual stars. Star formation proceeded gradually, building galaxies piece by piece over hundreds of millions of years. The resulting galaxies were messy, irregular structures filled with gas, dust, and young stars, nothing like the organized spirals and ellipticals we see in the modern universe. But sometimes gravity won decisively. If gas remained cool enough or if inflow rates exceeded certain thresholds, collapse could proceed without interruption. The entire cloud would plunge toward the center, reaching densities where nuclear fusion should ignite. But if the mass exceeded certain limits, fusion could not generate enough pressure to halt collapse. The cloud would bypass the star formation stage entirely, collapsing directly into a black hole. This is how massive seeds likely formed. The concentration of mass before galaxy formation explains the unusual black hole to galaxy mass ratios observed in early universe systems. Black holes formed first from the most rapidly collapsing gas. Then galaxies assembled around these existing black holes from remaining material. The black holes had a head start. By the time significant star formation began, black holes already dominated the gravitational potential at galactic centers. They grew faster than their host galaxies, creating the extreme ratios we now observe. Simulations confirm this sequence of events. When researchers model early universe structure formation in detail, black holes naturally form before galaxies in certain high-density regions. The process is not universal. Most regions formed stars first, then black holes from stellar collapse. But in a fraction of cases, perhaps 10 to 20%, direct collapse created massive black holes that predated their host galaxies. These early black holes then shaped how their galaxies evolved, influencing star formation through feedback from the moment galaxies began to form. Yet despite this understanding, our ability to find these objects remains frustratingly limited. Imagine trying to find a single dark pebble in a cave with only a weak flashlight. The pebble does not glow. It does not make noise. It only exists, small and hidden among countless other rocks. This describes the challenge of finding dormant black holes in distant galaxies. We cannot see them directly. We can only detect their effects on surrounding material. And if those effects are subtle, we miss them entirely. The dormant giant Webb discovered was detectable because its mass was enormous. 400 million stellar masses create gravitational effects strong enough to identify even at tremendous distances. Stars orbiting this black hole move at thousands of miles per second. That velocity produces spectroscopic signatures, detectable with Webb's instruments. Gas near the event horizon, even while accreting slowly, produces faint but measurable emission. The combination of high mass and sensitive instruments made detection possible. Now consider a dormant black hole with 1/10 the mass, 40 million stellar masses. Still enormous by any reasonable standard, but its gravitational effects scale down proportionally. Stars orbit slower. Spectroscopic signatures become weaker. The faint glow from minimal accretion drops below detection thresholds. With current technology, this black hole would be invisible despite existing in the same galaxy survey. It contributes to the galaxy's gravitational potential, influences star formation through past feedback, but leaves no trace we can currently measure. The detection threshold for dormant black holes sits around 100 million stellar masses at the distances of early universe galaxies. Below this limit, signals become too weak to distinguish from background noise. Measurements have uncertainties. Galaxies contain other sources of motion and emission. Separating black hole signatures from stellar populations requires strong, clear signals. Marginal detections are scientifically useless because alternative explanations cannot be ruled out. Only unambiguous measurements count. This means we are systematically missing most dormant black holes. Statistical models based on black hole mass distributions suggest that for every black hole above 100 million stellar masses, there should be roughly 5 to 10 black holes above 50 million, and 20 to 50 black holes above 25 million. The population pyramid is vast. We see only the peak. The base remains completely hidden. Most dormant black holes in the early universe are simply too small to detect with current methods. Future instruments might push detection limits lower. Larger telescopes collect more light. Better spectrographs achieve higher precision. Advanced data analysis techniques squeeze more information from existing observations. The European Extremely Large Telescope might reach 50 million stellar mass dormant black holes. A next-generation space telescope could go lower still. But there will always be a flaw. Below a certain mass, dormant black holes produce effects indistinguishable from normal galaxy dynamics. They exist, warping space silently, but remain fundamentally undetectable, which forces us to reconsider what we think we know about cosmic structure. Maps of the early universe show galaxies as bright spots scattered across darkness. Each point represents a galaxy detected through its light emission. Astronomers catalog positions, distances, masses, and properties. From these catalogs, we reconstruct the large-scale structure of the cosmos. Filaments of galaxies connected by dark matter. Voids where few galaxies exist. Clusters where hundreds of galaxies congregate. The map appears complete, comprehensive, reliable. It is none of those things. Every map contains only what we can detect. Active galaxies with vigorous star formation glow brightly. We spot them easily. Quiescent galaxies with older stellar populations appear fainter but still visible. We include them after careful observations. But dormant black holes, despite potentially outnumbering detectable galaxies, remain absent from our maps. They are there in reality but missing from our picture. We are mapping a universe with most of its massive objects invisible. This is not a small correction. If 90 to 95% of supermassive black holes spend most of their time dormant, and if most of those dormant black holes fall below detection thresholds, then we are missing critical components of cosmic structure. Black holes contribute gravitational mass. They influence how galaxies move, how structures form, how gas flows through space. Leaving them out of models is like trying to understand traffic patterns while ignoring most of the vehicles. The implications affect multiple areas of research. Galaxy formation models must account for black hole masses that vastly exceed what surveys detect. Predictions of how galaxies merge, how star formation proceeds, how feedback operates, all require accurate black hole populations. If our census is wrong by a factor of 10, every model built on that census is proportionally wrong. We have been working with incomplete information, drawing conclusions from partial data. Gravitational effects provide indirect evidence for missing mass. When astronomers measure how fast galaxies move in clusters, the velocities often exceed predictions based on visible matter. We attribute most of this discrepancy to dark matter, which is correct, but some fraction might come from dormant black holes contributing mass without light. The difference is small but not negligible. In regions with unusually high black hole concentrations, their collective mass could affect large-scale dynamics measurably. Cosmic census corrections cascade through astronomy. If black holes are more common than thought, then feedback from black holes played a bigger role in galaxy evolution than models suggest. If dormant black holes pervade the early universe, then the epoch of galaxy formation was shaped more by black hole activity than by star formation alone. The universe we reconstruct from observations depends on what we can see. When major components stay hidden, our reconstruction diverges from reality. We are looking at shadows on a cave wall, mistaking them for the objects casting those shadows. And one of the most important shadows involves how these black holes control their own food supply. Star formation requires cold gas. When gas cools below a few hundred degrees, it can collapse under its own gravity. Small regions become denser, eventually reaching conditions where nuclear fusion ignites. A star is born. This process repeats across a galaxy, wherever cold gas accumulates. Galaxies with abundant cold gas form stars rapidly. Galaxies lacking cold gas become dormant, their star formation halting. Black holes regulate this cycle by controlling gas temperature. Active black holes pump tremendous energy into their surroundings. Radiation from the accretion disk heats nearby gas directly through absorption of photons. But this heating affects only the immediate vicinity. The real galaxy-wide impact comes from winds. As gas spirals toward the event horizon, some gets ejected outward in powerful jets and winds traveling at thousands of miles per second. These winds carry kinetic energy, momentum, and sometimes magnetic fields. When they slam into surrounding gas, they deliver a shock that heats everything in their path. The heating is not subtle. Gas temperatures can jump from hundreds of degrees to millions of degrees in the wind-heated regions. At these temperatures, gas pressure overwhelms gravity. The gas expands rather than collapses. Star formation becomes impossible. The black hole has effectively sterilized its environment, preventing new stars from forming anywhere the winds reach. In small, early universe galaxies, winds can affect the entire galaxy. Star formation drops to near zero. The galaxy becomes quenched. This explains the suppressed star formation rate in galaxy GN-1001830. During past hyperactive feeding episodes, the black hole would have driven powerful winds that heated the galaxy's gas reservoir. Even though the black hole is now dormant and no longer actively heating gas, the gas remains hot. Cooling takes time. Hot gas radiates energy gradually through atomic processes, losing heat over tens of millions of years. Until the gas cools below star formation thresholds, the suppression continues. The effect is self-regulating in an interesting way. Active black holes suppress star formation, which reduces the gas supply available for future black hole feeding. The black hole essentially depletes its own food source through feedback. Once gas runs out, the black hole goes dormant. During dormancy, gas slowly cools and accumulates. Eventually, enough cold gas concentrates near the black hole to restart accretion. The black hole wakes up, feeds actively, heats the gas, suppresses star formation again, and the cycle repeats. This is how black holes and galaxies co-evolve. The cycle duration depends on gas cooling times and galaxy mass. Small galaxies have weaker gravity, making it easier for winds to blow gas out completely. Gas expelled from these galaxies takes longer to return, extending the dormant period. Large galaxies retain more gas, allowing faster recovery. But across all galaxy sizes, the basic pattern holds. Black holes alternate between active and dormant states, driving corresponding cycles in star formation. The galaxy breathes, expanding and contracting its stellar population in response to its central black hole, and detecting these cycles requires separating different sources of light with extraordinary precision. Light from a distant galaxy arrives mixed together. Photons from the black hole's accretion disk combine with photons from billions of stars, from glowing gas clouds, from dust reflecting starlight. Everything reaches Webb's mirrors simultaneously. To study the black hole separately, researchers must untangle this mixed signal. The technique is called spectral decomposition, and it requires both sophisticated instruments and careful analysis. Webb's near-infrared spectrograph splits incoming light into its component wavelengths with extreme precision. Each wavelength gets directed to a different pixel on the detector array. The result is a spectrum showing intensity at every wavelength from 0.6 to 5.3 microns. This spectrum contains overlapping contributions from multiple sources. Stars produce certain patterns. Gas clouds produce others. The black hole's accretion disk produces a third pattern. The challenge is separating them. Scientists use template spectra to identify components. They have catalogs of how different sources emit light. Old stars produce specific patterns based on their surface temperatures and compositions. Young stars produce different patterns dominated by strong emission lines from surrounding ionized gas. Accretion disks around black holes produce characteristic broad emission lines from rapidly moving gas. By fitting combinations of templates to observed spectra, researchers determine how much light comes from each source. The fitting process uses statistical methods to find the best match. Computers test millions of combinations, varying the relative contributions of different components. Each combination produces a predicted spectrum. The algorithm compares predictions to observations, calculating a goodness of fit score. Better matches get higher scores. After testing all combinations, the best fit reveals the composition. For galaxy GN-1001830, the best fit included a small contribution from a low luminosity accretion disk, plus larger contributions from stellar populations. Additional information comes from comparing different regions of the galaxy. Stars spread throughout the galaxy, producing relatively uniform light. The black hole occupies only the very center, producing concentrated emission from a tiny region. By comparing spectra from the central region to spectra from outer regions, researchers isolated the black hole's contribution. The central region showed unique features not present elsewhere. These features confirmed the presence of an active but faint accretion disk. The technique also used multiple camera filters to separate light by wavelength before spectroscopy. Webb's near-infrared camera can take images in various narrow wavelength bands. By subtracting images taken at different wavelengths, researchers highlighted specific emission processes. The black hole's accretion disk emits strongly in certain bands corresponding to hot gas emission. Subtracting images taken on either side of these bands revealed the spatial distribution of black hole light. It concentrated in a tiny central point, exactly as expected. This multi-method approach provided redundant confirmation. The dormant black hole was real, detectable, and precisely characterized. But how it could grow so fast required understanding physics that textbooks claimed was impossible. The Edington limit represents a balance. A black hole pulls matter inward through gravity. That matter heats up, producing radiation. Radiation exerts pressure outward, pushing against infalling material. When radiation pressure equals gravitational pull, equilibrium is reached. Matter can no longer fall inward faster because radiation blows it away. This defines the maximum steady-state accretion rate, or so astronomers thought for decades. Recent observations and simulations reveal the Edington limit is not absolute. It applies to steady-state conditions where gas flows in smoothly at constant rates. But the early universe was anything but steady. Gas clouds were turbulent, clumpy, and highly variable. Under these chaotic conditions, black holes can temporarily exceed the Edington limit through several mechanisms that bypass normal stability constraints. One mechanism involves optically thick inflow. If gas is dense enough, radiation cannot escape easily. Photons scatter off atoms multiple times before reaching the edge of the infalling material. This traps radiation inside the flow, preventing it from exerting outward pressure efficiently. The gas can continue falling inward despite producing radiation that would normally halt accretion. The black hole grows rapidly while the radiation remains trapped, only escaping after the gas crosses the event horizon. This allows growth rates 5 to 10 times higher than the Edington limit predicts. Another mechanism exploits magnetic fields. Simulations show that strong magnetic fields threading the accretion disk can channel gas directly toward the black hole along field lines. This focused inflow creates narrow streams moving at high speeds. Radiation pressure affects the broad disk, but not the narrow streams. Gas in the streams falls inward rapidly, bypassing regions where radiation would normally halt accretion. The streams contribute mass without triggering the feedback that limits steady-state growth. Clumpy accretion provides a third path. If gas approaches in dense clumps rather than smooth flows, each clump can penetrate closer to the black hole before radiation pressure affects it. Small clumps heat up and get blown away, but large, dense clumps have enough mass and momentum to push through. They deliver material directly to the black hole's immediate vicinity, where it quickly crosses the event horizon. The net result is higher average accretion rates than smooth flow models predict. These mechanisms do not operate indefinitely. Eventually, the black hole heats surrounding gas enough to disrupt the special conditions enabling super Eddington growth. Optically thick inflows become optically thin as material depletes. Magnetic field structures decay through turbulence. Clumps fragment or merge. The burst ends, and the black hole returns to sub-Eddington accretion or dormancy. But while the burst lasts, growth proceeds at remarkable rates. This is how the dormant giant reached 400 million stellar masses in just 800 million years. The question now becomes, what else might Webb discover as it continues surveying deeper regions of space? The dormant giant was found in a relatively shallow survey. The JADES program targeted galaxies out to about 13 billion light-years, corresponding to roughly 1 billion years after the Big Bang. Deeper surveys reaching farther back in time will probe the universe at 600, 400, even 200 million years after its beginning. These epochs witnessed the first galaxies forming, the first stars igniting, the first black holes appearing. Nobody knows what Webb will find there. Several competing theories make different predictions. If black holes form primarily from stellar collapse, then the earliest black holes should be small, no more than hundreds of stellar masses. They would grow over time, becoming larger at later epochs. This predicts a correlation between black hole mass and cosmic age. Early objects should be systematically smaller than later ones. Finding massive black holes at very early times would falsify this model. If direct collapse dominates, massive black holes should appear very early, potentially as soon as 200 million years after the Big Bang. These objects would be rare but dramatic, each one weighing millions of stellar masses upon formation. They would grow rapidly through subsequent accretion, potentially reaching billions of stellar masses by 1 billion years after the Big Bang. This model predicts massive black holes throughout the early universe, with the most massive ones appearing earliest. A hybrid scenario suggests both processes occur. Stellar collapse creates small black holes everywhere. Direct collapse creates massive black holes in special high-density regions. The population contains a mix, with smaller black holes dominating numerically but massive black holes dominating by total mass. This model best matches current observations but remains unconfirmed because our sample size is still small. A few dozen detections cannot distinguish between models reliably. Future surveys will provide the data needed to test these ideas. Webb is scheduled to continue deep field observations for at least 5 more years, potentially longer if the mission is extended. Each deep field contains thousands of galaxies spanning cosmic history. Systematic searches for dormant black holes in these fields will build a statistical sample large enough to reveal population trends. Do black hole masses increase with time, as stellar collapse predicts? Or do massive black holes appear at all epochs, as direct collapse suggests? The surveys might also find exotic objects predicted by theory, but never observed. Intermediate mass black holes between stellar mass and supermassive could exist if direct collapse produces a range of outcomes. Hypercompact dwarf galaxies containing very massive black holes in extremely small galaxies might represent failed galaxy mergers. Binary black holes orbiting each other, destined to eventually merge, could reveal the role of mergers in building supermassive black holes. Each discovery would refine our understanding of black hole physics and cosmic structure formation. But regardless of what we find, the implications for black hole evolution timeline S are already clear. Astronomy textbooks will need new chapters. The standard timeline for supermassive black hole formation started with massive stars collapsing roughly 200 million years after the Big Bang. These stellar mass black holes, weighing 10 to 100 stellar masses, would then grow through steady accretion at rates limited by the Edington constraint. After billions of years, some would reach millions of stellar masses. After many billions of years, a few would reach billions of stellar masses. This gradual process explained black holes in nearby galaxies nicely. It failed completely for early universe black holes. Objects like the dormant giant exist less than 1 billion years after the Big Bang, yet already weigh hundreds of millions of stellar masses. The old timeline cannot accommodate them, starting from stellar mass seeds and growing at the Edington limit for 800 million years, produces black holes of only 10,000 to 100,000 stellar masses. Off by 3 to 4 orders of magnitude, the observations and theory were incompatible. The new timeline incorporates burst growth and massive seeds. Black holes form through either stellar collapse or direct collapse between 100 and 400 million years after the Big Bang. Direct collapse creates massive seeds weighing 100,000 to 1 million stellar masses immediately. These seeds begin accreting surrounding gas. Under early universe conditions, dense gas and frequent mergers drive episodic super-Eddington accretion. Black holes grow explosively for 5 to 10 million year bursts, reaching 10 to 100 million stellar masses within 200 million years of formation. Multiple burst episodes continue as galaxies evolve. Each burst adds mass rapidly. Between bursts, dormancy periods last 100 million years or more. But the cumulative growth over multiple cycles builds supermassive black holes reaching hundreds of millions to billions of stellar masses within the first billion years. By 1 billion years after the Big Bang, the most massive black holes have already reached sizes comparable to black holes in modern large galaxies. Growth continues at later times, but at slower average rates. This timeline explains observations across cosmic history. Early universe black holes appear massive because they experienced multiple burst episodes in rapid succession. Later universe black holes appear smaller relative to their age because bursts become less frequent as gas densities decrease. Modern black holes grow primarily through steady accretion and mergers, rarely exceeding the Eddington limit. The universe has calmed down. Early chaos has given way to later stability. The revision affects more than just black hole formation. Galaxy evolution models must account for massive black holes appearing early and influencing star formation from the beginning. Cosmological simulations must include burst accretion to reproduce observed black hole populations. Theories of quasar formation, galaxy mergers, and large-scale structure all require updates to incorporate the new understanding. Every model, built on the old timeline, needs revision. The field is undergoing a paradigm shift, driven by observations that refuse to fit previous frameworks. And the biggest question of all remains unanswered. Look up at the night sky. Stars visible to your naked eye number in the thousands. Galaxies visible through amateur telescopes number in the millions. Each galaxy likely contains a supermassive black hole at its center. That is millions of cosmic monsters scattered across the visible universe. How many of them are actively feeding right now? How many are dormant? The answer might surprise you. If the burst model holds true universally, then 90 to 95% of black holes should be dormant at any given moment. Active feeding lasts 5 to 10 million years. Dormancy lasts 100 million years. Do the math. At any instant, you are 20 times more likely to catch a black hole sleeping than feeding. This ratio applies to the early universe where observations are best. It might also apply locally, though our census of nearby black holes is more complete, making the ratio easier to verify. Current surveys of the local universe find that about 5 to 10% of galaxies show signs of active black holes. These active galactic nuclei emit X-rays, radio waves, and visible light characteristic of ongoing accretion. The remaining 90 to 95% of galaxies appear quiet. Their central black holes produce minimal emission. We assumed these were small black holes growing slowly. The dormant giant discovery suggests many are large black holes sleeping temporarily. We have been misinterpreting silence as absence rather than recognizing it as dormancy. If true, the universe contains far more massive black holes than surveys indicate. Every quiet galaxy might host a sleeping monster. Some may never wake up again if gas supplies are exhausted. Others will eventually resume feeding when fresh gas becomes available through mergers or infall. But at this moment, the vast majority are silent, invisible, detectable only through their gravitational effects on surrounding stars and gas. We are surrounded by sleeping giants. This changes how we think about cosmic structure. Black holes are not rare exotic objects confined to a few special galaxies. They are common, perhaps universal, components of galactic centers. Their feedback shapes galaxy evolution even when dormant because dormancy follows active periods that already affected the galaxy. The scars of past activity persist long after the black hole sleeps. Galaxies carry histories written by their central black holes, visible in suppressed star formation, disturbed gas dynamics, and chemical compositions. The implications extend beyond astronomy. If most black holes spend most of their time dormant, then most of the universe's gravitational mass in compact objects is currently dark. These objects warp space-time, affect gravitational waves, and contribute to the large-scale structure of the cosmos without producing electromagnetic radiation. We are mapping a universe where most of the massive players are invisible. Our picture remains incomplete, and it will stay incomplete until technology advances enough to detect dormant black holes across all masses and distances. The dormant giant Webb discovered represents a turning point. It proved these objects exist, can be found, and follow patterns predictable by theory. Future discoveries will build on this foundation, gradually revealing the hidden population. Decades from now, we might have a complete census, but today, we must accept that most cosmic monsters are asleep. The universe is quieter than we thought, but far more populated. And somewhere in the darkness, 800 million light-years away, a black hole 400 million times more massive than our closest star continues its long nap, waiting for the gas to return. James Webb did not just appear in space fully formed. Decades of engineering, billions of dollars, countless setbacks, and the work of thousands of scientists preceded its launch. The telescope represents humanity's most ambitious attempt to see the invisible, to capture light that has traveled across most of cosmic history. Without specific technological advances, the dormant giant would have remained hidden forever, just another faint smudge in an overcrowded sky. The primary mirror makes everything possible. Webb's mirror spans 21 feet across, composed of 18 hexagonal segments made from beryllium coated in gold. Each segment can be individually adjusted to nanometer precision, maintaining perfect alignment despite temperature fluctuations in space. The mirror's size matters because light-gathering power scales with area. Bigger mirrors collect more photons. More photons mean fainter objects become detectable. Webb's mirror collects 6 times more light than Hubble's, pushing detection limits dramatically farther into space and time. But size alone does not explain the breakthrough. Webb operates in infrared wavelengths, not visible light. This choice was deliberate and essential. Light from distant objects stretches as the universe expands, shifting to longer wavelengths through a process called redshifting. The galaxy hosting the dormant black hole emitted ultraviolet and visible light 800 million years after the Big Bang. By the time that light reached Earth, expansion had stretched it into infrared. Hubble, designed primarily for visible light, could barely detect it. Webb sees infrared naturally, making distant early universe objects appear bright and clear. Cooling systems keep the instruments at negative 380 degrees Fahrenheit. Infrared detection requires extreme cold because heat itself produces infrared radiation. If the telescope were warm, its own heat would drown out faint signals from space. A massive sun shield, the size of a tennis court, blocks heat from our star, Earth, and Moon, maintaining the frigid temperatures needed for sensitive observations. Without this shield, background noise would overwhelm every measurement. The near-infrared spectrograph provided the crucial data for identifying the black hole. This instrument splits light into thousands of individual wavelengths with extraordinary precision. Each wavelength gets measured separately, creating detailed spectra that reveal composition, temperature, density, and motion. The spectrograph detected the broad emission lines, characteristic of gas, orbiting a massive black hole, moving at thousands of miles per second. No other instrument in human history could have captured this data from such a distant, faint object. Data transmission and analysis complete the chain. Webb sits 1 million miles from Earth at a special gravitational balance point called L2. Information travels back through the deep space network, massive radio dishes scattered across the globe. The raw data requires processing through sophisticated algorithms to remove noise, calibrate instruments, and extract meaningful signals. Teams of scientists then analyze processed data, comparing observations to theoretical predictions. Every step in this chain must work perfectly. One failure anywhere would have hidden the dormant giant. But every link held. The detection succeeded, and what it revealed about how black holes interact with the hidden universe is profound. Dark matter outweighs normal matter 5-to-1 throughout the universe. It does not emit light, does not absorb light, does not interact through electromagnetic forces. Gravity is its only calling card. We know dark matter exists because galaxies rotate too fast. Stars in outer regions orbit at speeds that should fling them into space. If only visible matter provided gravitational pull. Something invisible must be adding mass, creating enough gravity to hold galaxies together. That something is dark matter. Early universe structure formation depends critically on dark matter distribution. Dark matter clumped first after the Big Bang, forming halos where normal matter would later accumulate. These halos acted as gravitational seeds, determining where galaxies would form and how massive they would become. Larger dark matter halos attracted more gas, producing larger galaxies. Smaller halos produced dwarf galaxies. The relationship between dark matter and normal matter shaped cosmic structure across all scales. The dormant black hole complicates this picture in subtle but important ways. Its host galaxy is tiny, containing only 830 million stellar masses. For such a small galaxy to host a 400 million stellar mass black hole suggests either the dark matter halo is unusually massive for the galaxy size, or the black hole formed through processes independent of dark matter distribution. Both possibilities challenge standard models connecting dark matter halos to galaxy properties. One scenario involves a stripped galaxy. Perhaps this system originally existed within a much larger dark matter halo containing billions of stellar masses worth of normal matter. Early interactions with neighboring galaxies could have stripped away most of the stars and gas, leaving behind only the central region containing the black hole. The dark matter halo would have been partially stripped as well, but dark matter's lack of friction makes it harder to remove completely. The galaxy we observe might be a remnant, the leftover core of a once larger system. Another possibility suggests the dark matter halo is intact but unusually concentrated. Simulations show that dark matter distributions vary significantly. Some halos have shallow density profiles with mass spread widely. Others have steep profiles with mass concentrated centrally. A highly concentrated halo could explain how enough gas accumulated in the center to form a massive black hole before significant star formation occurred. The black hole to galaxy mass ratio would naturally be extreme in such systems because most of the mass concentrated where the black hole formed. Testing these scenarios requires gravitational lensing measurements. When light from background objects passes near the galaxy, the combined gravity of stars, gas, dark matter, and the black hole bends that light, creating distortions. The pattern of distortion reveals the total mass distribution, including dark matter. Future observations targeting this galaxy and similar systems will map their dark matter halos, determining whether they are stripped remnants or intact but concentrated. The answer affects how we model the relationship between dark matter, galaxies, and black holes throughout cosmic history. But perhaps more dramatic than these structural questions is what happens when dormancy ends. Silence ends violently. The black hole has slept for 100 million years, consuming almost nothing, producing barely any light. Gas has been accumulating slowly, drifting inward through gravitational attraction. The accretion disk has grown thicker, denser, more massive. Now it reaches a critical threshold. The dormant giant stirs. Accretion accelerates. The awakening begins. First comes the brightening. Gas closer to the event horizon heats to millions of degrees through friction and compression. Atoms collide at tremendous speeds, releasing energy as radiation. The accretion disk begins glowing, first in infrared, then visible light, then ultraviolet and X-rays as temperatures climb. Within a few thousand years, the black hole's luminosity increases 1,000-fold. From Earth, if we could observe this galaxy in real time, it would appear to suddenly brighten like a cosmic lighthouse. Switching on, winds follow quickly. Radiation pressure from the glowing disk pushes outward on surrounding gas. But that is just the beginning. Magnetic fields threading the accretion disk launch jets of energetic particles from the poles. These jets move at nearly the speed of light, carrying tremendous energy away from the black hole. They slam into surrounding gas, heating it, compressing it, driving powerful shocks that ripple outward through the galaxy. The black hole has become an engine, converting gravitational potential energy into kinetic energy and radiation. Star formation responds within a few million years. The winds heat gas throughout the galaxy, raising temperatures above thresholds where stars can form. Cold molecular clouds that might have collapsed into new stars get disrupted, heated, and dispersed. Star formation rates plummet. The galaxy transitions from actively forming stars to quiescence. This feedback is self-regulating. By suppressing star formation, the black hole limits future gas supplies, ensuring it will eventually exhaust its food and return to dormancy. But for now, it feeds voraciously. The feeding phase lasts 5 to 10 million years if the black hole enters super Eddington accretion. During this time, it might double or triple its mass, growing from 400 million to 800 million or even 1 billion stellar masses. The growth is dramatic and rapid by cosmic standards. Astronomers observing from afar would see a quasar, one of the brightest objects in the universe, outshining all stars in the host galaxy combined. The black hole would dominate every measurement, its light overwhelming everything else. Then the feast ends. Gas reserves deplete. Winds have blown material away. The accretion disk thins. Luminosity drops. Within a few 100,000 years, the black hole fades back into dormancy. The cycle completes. The galaxy is left transformed. Its gas is hotter, more dispersed, less available for star formation. Chemical composition has changed through ejection of material processed near the black hole. Structure has been altered by winds and shocks. The black hole leaves permanent marks even after going silent. And billions of years later, these brief, active episodes determine what galaxies look like today. Galaxy clusters dominate the modern universe. These massive structures contain hundreds or thousands of galaxies bound together by gravity, spanning millions of light years. The largest clusters weigh as much as 1 million billion stellar masses, making them the most massive gravitationally bound structures in existence. Every large cluster contains a central giant elliptical galaxy. And every giant elliptical galaxy contains a supermassive black hole weighing billions of stellar masses. The connection is not coincidental. Simulations show that early universe black holes seed the formation of these massive systems. The dormant giant discovered by Webb existed in a small galaxy 800 million years after the Big Bang. That galaxy did not stay small. Over billions of years, it merged with other galaxies, growing through collisions and acquisitions. Each merger added stars, gas, and dark matter. The galaxy grew from millions to billions to trillions of stellar masses. Its central black hole grew proportionally, accumulating mass from each merger. The black hole's early head start matters critically, because it already weighed hundreds of millions of stellar masses very early. It dominated gravitational dynamics at the center of each merger. Smaller black holes from infalling galaxies either merged with it or were ejected through gravitational slingshot interactions. The dominant black hole won every encounter, consolidating mass at the cluster center. By the modern era, it would weigh billions of stellar masses, comparable to the most massive black holes we observe in nearby galaxy clusters. The feedback history from this black hole shaped the entire cluster. During multiple active phases across billions of years, the black hole drove winds and jets that heated gas throughout the protocluster. This heating prevented gas from cooling and forming stars, keeping much of the cluster's mass in hot diffuse form rather than locked in stars. Observations of modern clusters reveal exactly this pattern. They contain vast amounts of hot gas visible in X-rays, but relatively few stars for their total mass. Black hole feedback explains the discrepancy. Specific clusters might trace directly back to objects like the dormant giant. The Phoenix cluster, for instance, contains a central galaxy with a black hole weighing roughly 20 billion stellar masses. Tracing its history backward through cosmic time requires accounting for all the mergers, all the growth episodes, all the feedback events. Computer simulations, starting from early universe conditions, produce clusters with properties, matching observations only if they include massive seed black holes forming early. Without those seeds, clusters evolve differently, producing central galaxies and black holes that look nothing like what we see. This establishes a direct connection between Webb's discovery and structures we can observe in detail today. The dormant giant represents an early stage of objects that evolved into modern cluster central galaxies. By studying these early systems, we learn about the origins of the most massive structures in the universe. We are watching the seeds of galaxy clusters during their initial growth, seeing the processes that will eventually produce the giants that dominate the cosmic landscape billions of years later. And these massive objects produce signals we are only just learning to detect. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate. Einstein predicted their existence over a century ago. Scientists finally detected them in 2015 using LIGO, the Laser Interferometer Gravitational Wave Observatory. That first detection came from two stellar mass black holes merging, each weighing about 30 stellar masses. Their collision released more energy in gravitational waves in 1 second than all the stars in the observable universe emit as light. The detection opened a new window on the cosmos. Supermassive black hole mergers produce gravitational waves at much lower frequencies. When two galaxies collide, their central black holes eventually spiral together and merge. A collision between 2 billion stellar mass black holes would produce gravitational waves oscillating at thousandths of a hertz, far below LIGO's detection range. Different instruments are needed. LISA, the Laser Interferometer Space Antenna, will launch in the 2030s specifically to detect these low-frequency waves. Its sensitivity range perfectly matches supermassive black hole mergers. The dormant giant discovery affects LISA predictions significantly. Previous models assumed supermassive black holes grew slowly and steadily, reaching hundreds of millions of stellar masses only in the late universe. These models predicted relatively few massive black hole mergers in the early universe. LISA would primarily detect mergers from recent cosmic history, events occurring within the past few billion years. Detection rates were estimated at a few per year across the entire observable universe. But if massive black holes formed early and were common, as the dormant giant suggests, then early universe merger rates were much higher than predicted. Galaxy mergers were frequent in the first billion years. If most galaxies hosted massive black holes during this era, then black hole mergers accompanied most galaxy collisions. The rate could have been 10 to 100 times higher than steady growth models suggested. This dramatically increases expected detection rates for LISA. Early universe mergers produce weaker signals because of cosmological redshift. Gravitational waves stretch along with space as the universe expands. Waves from 800 million years after the Big Bang arrive at Earth, redshifted by factors of 10 or more, reducing their amplitude and shifting their frequency. They become harder to detect but not impossible. LISA's sensitivity should still catch the most massive early mergers. If the dormant giant population is real, LISA might detect dozens of early universe supermassive black hole mergers per year, instead of just a few late universe events. These detections would provide independent confirmation of the burst growth model. Gravitational waves carry information about black hole masses and spins. By measuring the properties of merging black holes across cosmic history, scientists can reconstruct black hole populations as they evolve. If we detect many massive black hole mergers in the early universe, it proves massive black holes formed early through direct collapse or burst growth. If we detect few early mergers, it supports slow, steady growth from stellar mass seeds. The gravitational wave data will settle questions that electromagnetic observations leave uncertain, and the stakes could not be higher. Our entire understanding of how structure formed in the universe depends on getting this story right. The dormant giant has shown us that the universe holds surprises in its darkest corners, hidden not because they are small, but because they are sleeping. The cosmos is filled with monsters waiting to be discovered,